Thank you very much for the invitation. It is a great honor to talk at this symposium on Don Perkins and on the other aspect, namely the neutral currents, in order to give you a complete picture of what his contributions are in neutrino physics. I know Don since 1968, and we remained in close contact more than 50 years. He once told me how he became a neutrino physicist. In the context of the big project at CERN of the ISR, the intersecting storage ring, he was invited as an expert to discuss what kind of physics could come out of that project. He got to know at that moment Colin Rum, who was the head of the NPA division at CERN nuclear physics apparatus. And later on, Colin invited Don to participate in the CERN neutrino program. So Don arrived just at the moment when the improved neutrino experiment, you have first of the failure of the first one, came into operation and made the first runs. And Don presented these first runs at the Siena conference. He made the first analysis of neutral currents, and he had observed 11 events with identified hadrons in the final state. You can see here in the black part. It was immediately clear what the real problem is. You have to show that these events are not background. Now, in the neutrino experiment, neutrons are an automatic background because the neutron is generated in the neutrino interaction, and then if it enters the chamber, it has the same topology as a neutral current event. Unfortunately, the dimensions of the chamber are of the same order than the interaction lengths of neutrons, so it was extremely difficult to make any numerical statement. So at the end, an upper limit was given of the elastic cross-section compared to the charge current elastic cross-section of 5%. For many people, this was a signal of probably those objects don't exist. Here is the report Bernardini, the director at that time, was giving, and you can see here the 5%. At the end of the conference in Siena, people were thinking about what came really out, and Lagarigue was one of them and said, well, the potential of this new field is extremely big, so we have to think of a new detector in order to get more statistics. The idea was to build a large bubble chamber, which became a Gargamel. And you know that the cross-sections, the number of events is proportional to the target mass. Therefore, you need a big chamber and also a heavy liquid. It was a cylindrical chamber such that you can distinguish by an interaction whether you are dealing with a muon or with a pion. So in the meantime, Lagarigue was forming the Gargamel collaboration consisting of 7 European laboratories: Aachen, Brussels, CERN, École Polytechnique, Milan, Orsay, and University College London. So you can see there is both experience in running a bubble chamber and on the other hand also experience in evaluating a neutrino experiment. At the Milan meeting, which was in October 1968, the dominant topic was the discovery of the proton's substructure at SLAC. Therefore, the outstanding question was, what could a neutrino experiment contribute? You see, you have at SLAC as a probe the electromagnetic current, and with a new experiment in future, you would have the weak charge current to find out what happens in the proton. The new tools are then to have a neutrino and an antineutrino. The exploration of the proton structure was therefore the main topic and on the priority list of the future experiment. It ranged really at top priority. On the other hand, since there was no evidence for neutral currents, it was not forgotten, but it was put on lowest priority. The Gargamel experiment, the chamber itself arrived during 1970, and the first expansion was in December 1970. Data taking started a few months later in neutrino and antineutrino wideband beam. The initial aim was indeed to measure the total cross-section and to investigate the nucleon structure. The data were taken on film and distributed amongst the 7 laboratories. It was obvious that in such a situation you need extremely strict rules for scanning and measuring, otherwise you cannot compare the data and putting the data together. This was done before the start of the experiment. The events were distributed in 4 categories: the regular neutrino events, such which have a muon candidate in the final state. Then a key category was those events which consist only of identified hadrons. These were supposed to be the neutrons, and these were important in order to correct particles, positive particles or negative particles, which are supposed to be a muon, but in reality are pion. Then there are events consisting of just 1 or more protons, and finally events with an isolated electron, positron, or photon. Here is the bubble chamber at its beginning, when it was assembled, and at the end, 1989, when a crack occurred, and therefore this defines the end of the bubble chamber. Here are some technical details. You can see longitudinal cross-section. The beam comes from the right, penetrates the ion shielding, and then enters into the fiducial volume, which is marked in blue. You can see that the chamber is within very heavy material, which will later be of great importance. The chamber was almost 5 meters long and had a diameter of 1.8, and so the fiducial volume was of 3 cubic meters, and therefore a big target mass. This ensured a high detection efficiency of the final state particles. The optical system, which is shown at the side, there are flashlights illuminating the tracks, and the pictures are transported through about 2 meters of the iron yoke. That needed to have very special scan tables and measuring tables. At 1971, Duft and Feldman proved the normalization, and at that moment, the Weinberg model attracted high attention. At this moment, it was clear that weak and electromagnetic interactions are on the same footing. However, there was no W, there was no Z, there was no Higgs, there was no neutral current. At the collaboration meeting, which took place a few months later, now the category B events demonstrated their important role. If neutral currents exist, they would already be present in the category B. So initially foreseen to get the neutron background, but here you have in addition the data, the new effect. If it is there, it is already there. The Milan group looked at the events which had only hadrons in the final state and had the observation that there was no exponential fall off. Now, in a very long bubble chamber, it is clear that the interaction length is only 70 or 80 centimeters. Therefore, you won't have any events if they are due to neutral currents. Sorry, if they are, yes, if if there are neutral currents, they would surely appear in the second part of the bubble chamber. Now, from that moment on, it was a decision to make a dedicated search for neutral currents, both in leptonic and in hadronic channels. And so the analysis continued simultaneously with both neutral and charged current. Just a few weeks later, Don Perkins wrote a memo where he recapitulated all the knowledge gathered in the previous neutrino experiments and distributed that to the neutrino collaboration. Here you can see here. In order to interpret the data, he used a very simple model, a linear model, just assuming that any neutrino interaction emits a neutron just in the same direction as a beam. Then a neutron interaction can appear in two ways. If you observe a neutral star, it is either associated to its source, the neutrino, or else the source is outside. So these events have been called in our jargon as B events, background events, and associated events. It is very easy to calculate it because what enters is the interaction probability of a neutron in the liquid and the ratio of the mass effects of the two media. Now, what are the lessons from the previous experiments? He had the thesis of his PhD student Enoch Young. You have already heard about him. A full analysis of the data. Then, 1967, there was a second run with propane in the chamber. There, the advantage was that you have not only bound protons, but also free protons. And a very important insight came that the initial value of the 5% you have seen before was underestimated because single unidentified positive tracks were taken as pions. And that explained very well why it is so small. So the reanalysis with all the data showed that in reality the ratio in the elastic and the one pion channel was quite big, 12 plus or minus 0.06 or 0.08 and plus or minus 0.04. This was published then in the paper by Candy et al. Don Perkins, on the basis of this very simple model, evaluated the neutron background. This evaluation is simple because the only thing you need is the calculated B/S ratio and the number of associated events. So the product of the two is a prediction of how many neutrons background events you are expecting. Now, you can see here in the case of Freon, there were 38 events compared to predicted 12, and in propane, 79 compared to predicted 31. Unfortunately, this excess cannot be interpreted as a discovery because the model was far too simple. So Perkins' conclusion was the existing data are indicative but not conclusive. The prospects for a discovery, we are still at the beginning of 1972, with Gargamel looks promising because of the length of the chamber. And a very strong warning was given to him, watch the neutron background. This is, I quote from his memo, although I know that many people at CERN are working on this problem, there appear to be innumerable pitfalls in the analysis, and a thorough discussion at an early stage would be well worthwhile. So the strategy for the analysis was very clear, and Oh, that was too much. How can I go back? Yes. The collaboration was very clear about the challenge they were given to. The signal was obvious, an event where there is no charged lepton. It was also clear what the background is. So the challenge consisted in proving that the number of background events is small compared to the number of candidates. It was also known that an American group was the Harvard, Pennsylvania, Wisconsin group was searching for the same effect, and so there was competition between them. So the collaboration felt very well the tension between being first and being right. At the end of the year, in December 1972, there was great excitement because an event was formed, which you can see as this most famous event from Gargamel. It was originally misclassified, and the PhD student in charge said, well, maybe it is an electron and not a muon with an overlated gamma. So he went up to the supervisor, which was Klaus Schulze, and Schulze looked at it. Well, that looks more like an electron. So they went up to Feisner, and Feisner, oh, that's just a discovery. And he immediately took the next plane to London, where Don Perkins was already waiting. And he waved the event in his hand, and Don Perkins was shouting, neutrino or antineutrino? When he answered antineutrino, they were very happy and had a big embracement. You can see here, when they celebrated the Aachen event, you can see in the middle the head of the neutrino group, and 2 persons later was Helmut Feisner, the director of the institute, and scanning girls. Here are 2 candidates, beautiful candidates of neutral currents. You can see direct by your eye the interactions, there was no doubt about it. Now, in March, so precisely 1 year later, Lagarrigue entered the CERN meeting with a big smile. He, in the meantime, 38,000 neutrinos and 207,000 antineutrino pictures have been scanned, and a sample of neutral current candidates consisting now of this one lepton event and 102 neutrino and 64 events in the antineutrino film. In order to make a direct comparison, a charged current sample was used where the muon was ignored, and exactly the same criteria applied to the final state of the event. Now, there was a clear expectation. If these events are all due to neutrons, then there must be a fall-off at the beginning, since the bubble chamber is much longer, 4 times longer than the interaction length of a neutron. So if you then observe events in the second part, you have a discovery. So the answer is, if they are all due to neutrons, then you must have a flat distribution. Therefore, there could be everything in between these 2. So if you look at the data, you can see that the ratio is very well consistent with being a constant, and therefore there was the intriguing situation. Have you made a discovery or not yet? So just at the end of this conference, 2 guys were standing up and said, wait, you have forgotten something. Namely, the neutrons make cascades. Therefore, it is not the interaction length which is relevant, but the cascade length, which can be much bigger. Therefore, the background can be much bigger. On the other hand, the neutrino flux is not just centering at the entrance window, but extending over the full range where lots of material is. This means that many more neutrino interactions are outside. If then by chance the neutron is emitted at a certain angle towards the chamber, it was filling completely the chamber, and therefore there was no distinctive feature left. So therefore the euphoria was damped, and there was no distinctive feature left, and we are back to the main problem, namely to prove that the background is much smaller than the number of candidates. This meant one had to make a prediction, a serious prediction of all the details of the experiment. And since you have seen the whole setup is very complex, only a Monte Carlo method was able to cope with this. We needed 5 different ingredients. One was the geometry of the setup, that was known. The matter distribution, that was also known. The neutrino flux was measured. The dynamics of the neutrino interactions could be taken directly from the experiment. So the real problem which remained was to propagate the final state particles during the whole material which was there. We were requested to come up with a result within a few weeks, because they were, many people were believing they had already made a discovery. Now, finally, a breakthrough came by recognizing that the meson component is inactive. So the only thing which was left is the elasticity of a proton or a neutron along its path. This required the probability how much energy is deposited and how much energy is transported away. This could be obtained from data directly, from proton-proton data or proton-neutron data, and therefore the result was an absolute prediction with no free parameter, which means if you make a prediction, then you stick out your head. Now, in July '73, so 4 months after the meeting at CERN, Puglia had finalized the number of associated events, and he came up with 15 neutrino and 11 antineutrino events. On the other hand, the neutron background program was also ready and predicted B over IS equals 1 plus or minus 0.3. Now, we made the worst possible hypothesis, saying that all candidates we have observed are due to background. In that case, you can directly calculate what B over IS is, namely 6.8 plus or minus 0.3, to be compared with the calculation, which is 1 plus or minus 0.3. So there was a huge discrepancy, and the hypothesis could be rejected, and the claim could be formulated that there is a new effect. See, all our collaborators, our colleagues in H1, in the Gargamel, were then thinking of flaws in the calculation. And this lasted for about 2 weeks of hot discussions, and finally everybody was convinced. The result was then presented by Musset in the CERN auditorium in July 19th, and a few days later, the paper was submitted in Physics Letters, while the other event was already published at the beginning of the year. Here are the authors of the discovery, 60 authors altogether, big collaboration. The result was then, the discovery was presented then at the Electron Photon Conference 1 month later in August 27 to 31, and Gerald Mayat was presenting the Gargamel data. He was asked to include also a last-minute contribution from the HPW group, and there was no discrepancy between these. In the parallel session by Fred Bullock, as speaker, the details were given. As soon as he opened his mouth, there was calorubia make an intervention and asking very nasty questions about the neutron background. We were very prompt in answering all these things. And finally, at the end, the epitome of C.N. Young, he stood up and said, neutron currents have been discovered. Now, unfortunately, this, I have to add, at the end of this, Rubia was waiting outside, and he said, I have given you hell, but I believe you are right. Now, his belief to be right lasted only a few weeks because the collaboration, the HBW collaboration, decided to postpone their publication and to make further runs to get more statistics. In order to do that, they introduced a 13-inch iron plate. Indeed, they got a bigger acceptance of muons, therefore a bigger number of events, but unfortunately, they lost the neutron current effect. And from that moment on, almost the rest of the world was saying, somebody must be wrong, it must be Gargamel. So we were treated with derision and with critics. Don Perkins met at some moment the Director General Jenschke, and he describes very well the situation which was there. So I will read it. It is published in the CERN Courier. When the claim to have found neutron currents in Gargamel was followed by the report from Fermilab that the NC over CC ratio they found was consistent with zero, many physicists believed that the Gargamel result must be wrong. Indeed, one senior physicist at CERN, well, everybody knows that was Steinberger, bet so heavily against Gargamel that he lost half of his wine cellar. But Jenschke himself was always very supportive of the experiment. I did meet him on one occasion in the CERN lift. He told me he was worried about the Gargamel result because some people had told him it could be wrong, and that would be very bad for CERN. My response, so Perkins' response was that coming after the split A2 affair, it would be an absolute disaster. However, I knew the group had gone through the event analysis many times, and for almost a year, we had searched intensively for some other explanation for the effect observed without success. So I thought the result was absolutely solid, and he should just ignore rumors from across the Atlantic. I don't know if my words reassured him, but he got out of the lift with a smile on his face. Now, the situation for the collaboration and for CERN became rather critical. It boiled down to the question, is the cascade program right or wrong? We need a decision. And this was obtained by sending pulses from the PS, proton pulses, directly into the chamber. So you can see with your eyes what the cascade is. And at the right side, you see a beautiful example of a 7 GeV proton entering, generating a very clear cascade. This, I had to make the prediction of what to be observed with these observed events beforehand. So it was clear what could happen. These are the result. We measured the apparent interaction length in the chamber, and you can see it is completely flat and around 80 to 90 centimeters, as expected. On the other hand, it's also clear that the cascade length is indeed increasing with energy, and it was excellent agreement with the absolute prediction. This was later on reported to the APS meeting in Washington. So all the aspects of the cascade are confirmed, and therefore all over happiness was there. The final acceptance was then reached in one year after the claim, namely in spring '74. After all, Gargamel was all the time right. We did not change one iota. Gargamel, in the meantime, doubled statistics, in agreement with previous results. Then there is a beautiful new experiment by Barry Barish in a narrowband neutrino beam, and single pion production has been observed. And finally, also the HBW group has confirmed the signal. And going from yes, no to yes, the joke came that they discovered the alternating currents. Now, with this discovery, Gargamel made an important contribution to high-energy physics, and CERN gained a leading role by this discovery. No, one before. I finish very quickly. The impact of the discovery was enormous. It may change the policy of all big laboratories to restructure their program in order to explore the new force. There were two immediate effects, namely due to the fact that the Z has now a coupling to two neutrinos, the gravitational collapse had a new argument. The other thing was the neutrino at 1906 at Aachen, the neutrino conference was taking place, and at that moment the sine squared theta was measured to plus or minus 0.05, and therefore within the simple Weinberg model, it was then easy to calculate, since there was only one free parameter, to calculate the mass of the W, which was 70 GeV. So it was clear that all the previous searches were just impossible. So neutrino experiment. Steinberger, for instance, in his said, if it is 20 GeV, I will discover it. But now you can see that was impossible. So this was the beginning of the P-P collider, which was proposed and which was realized then at CERN within 7 years. Now, if you look at the right side, you can see the beautiful electroweak way starting at 73 with the discovery of the Neutron currents and the W and the Z, and finally the Higgs. So at the end of this story is the standard model in its full glory. So this is the admired Don Perkins. You remember perhaps how he often said to us, physics is simple, but you make it sometimes very complicated. So thank you, Don.